Today we want to do some review for the upcoming test. Here's the first problem on the exam practice. Suppose we want to draw a direction field and integral curves with behaviors t goes to infinity for dy dt equals minus 1 minus 3y. What we want to do here is sketch a bunch of little line segments. That's the direction field. At each point in the ty plane, the solution plane, you have a little line segment of slope minus 1 minus 3y, the slope of the solution at each point. And the field of all line segments associated with the points, or you can draw arrows if you prefer, is called the direction field or slope field in the text. So how can we sketch those quickly? Because this can take a long time by hand. We can draw isoclines, one slope curves, and we can put the slope, let's say m equals minus 1 minus 3y. That is, minus 1 minus 3y equals a constant along each isocline. This is not the direction field. This is a construct for making the direction field. So let's put 0 equals minus 1 minus 3y. That corresponds to slope m equals 0. So we just put the right side equals 0. That gives us this isocline. This is y equals minus a third. It's actually a horizontal line in this case, right down here. So maybe here's minus a third, and I'll draw little dots here. We'll draw these little line segments. These are elements of the direction field. Each one of slope 0 at a point where the right side of the differential equation is 0. Now let's try m equals 1. Along this isocline, 1 equals minus 1 minus 3y. Equivalently, if you add 1 to each side and divide by 3, you get y equals minus 2/3. So we go down a little further to minus 2/3 on the y-axis. And everywhere along this isocline, the direction field segments will have slope 1. So now you draw a whole bunch of slope 1 segments. Something like that, maybe. And now you're starting to fill up the plane with these little line segments. The line segments are the direction field. These dots are the isoclines I'm using to sketch them. Let's put m equals, let's say, minus 2. Let's see, yeah, minus 2. Oh, minus 4, let's do that. All right, now I've got minus 4 equals minus 1 minus 3y. If I add 1 to each side, that's equivalently minus 3 equals minus 3y, or y equals 1. So along this line up here, here's another isocline. It happens to be a line. They don't have to be lines. Take a look at the example in the notes, for instance. Along this isocline, this curve here that I've drawn is a dotted curve. Every line segment in the direction field will have slope minus 4, so it's kind of steep like that. So there's some more elements of the direction field. Maybe I'll put now m equals minus 1. That's minus 1 equals the right side of the differential equation. Let's see, I add 1 to each side, and I've got minus 3y equals 0. That's just y equals 0. So the t-axis, y equals 0, is an isocline. Each point here, I have to draw a slope minus 1, maybe like this. And now the object is to use those and think of those as little ripples on a flowing stream. And how does the stream flow? It looks like it flows like this. It has to be tangent to this line, tangent to this line. Now, right, it has to have, when it passes a line segment of the direction field, it has to be tangent to it, because after all, this is the slope of the solution. Up here, the slope of the solution is the slope of this line segment also. Down here, if you have a solution, it comes up like this, and it's tangent to these. And so there is a sketch of some of the solutions, each one tangent to the direction field as though there's this flowing water, and you see the little ripples on here. And there's a solution right here where you have horizontal direction field segments, you have to have a horizontal tangent line to the curve, and these are all horizontal, so actually this whole line is a solution. So there they are. These don't actually intersect. If you had two intersect, then the point they intersect at could be an initial value, where the solution may not be unique. But for this nice function, f, if you like, f of ty in general, this time it just depends on y, it's an autonomous equation we call it. But when f and its partial derivative with respect to y are both continuous, as in this case, we recall corresponding to any initial value, we're going to get a unique solution, which means these can't intersect. Actually, if they did intersect over here, that would be one initial point that had two solutions coming out of it. So it would not be a unique solution out of there. So there is actually a solution curve going through every point here because of the existence of the solution. And they don't intersect because of uniqueness. And so we draw the picture like this, and now you can answer some of these other questions. Here's the direction field, all these little line segments. You could fill a whole plane with them. You kind of get the feel that over here they maybe look like that, up here they maybe look a little steeper. You can figure that out if you draw more of these direction field segments. And then integral curves are solutions. That's just a fancy name for solutions of an autonomous equation like that. So solution curves. And then with the behaviors, t goes to infinity, they behave like this. They move asymptotically. That's number one. Let me put number two up here and take a look at that. The question is, for this differential equation, what's the order? Well, you just look for the highest derivative. The highest derivative is second, so it's a second order equation. State whether the equation, let's put it off the end, making it so large, is linear or nonlinear. When it can be written as a function of t times y double prime plus a function of t times y prime plus a function of t times y equals a function of t only, and it can be higher order with another function of t times third derivative or something, and so on. Then it is a linear equation, so this one is linear. This one is not. Why not? Because the function multiplying the third derivative here is not a function of t only. It's y times this. If y multiplies the derivative, it's out, right? So this is not a function of t only. It's not a linear equation. It looks kind of like this one, but it's not linear. This is a third order equation because the third derivative is the highest that appears. How about this one? Verify that this given function is a solution to this differential equation. That's easy to check. You just take the first and second derivatives, plug in the first and second derivatives and y itself, and see that the equation is satisfied. We can do that pretty easily. Y prime equal, by taking the derivative e to the kt, has derivative k e to the kt, so this is 2 times minus 2 e to the minus 2t. That's by the chain rule, but you just memorize that one. Is minus 4 e to the minus 2t. Then y double prime is equal to, I got a room, is equal to the derivative of that. Minus 4 comes out, the derivative of e to the minus 2t is minus 2 e to the minus 2t again. So you get 8 e to the minus 2t. Now you plug those in to the left side. Plug in to the left, LHS to the left-hand side. Y double prime is 8 e to the minus 2t. Then I have to add 7y prime, which was minus 4 e to the minus 2t. And then I have to add 10y, 10 times 2 e to the minus 2t. And what have I got? Well, I got 8 minus 28 plus 20. 8 minus 28 plus 20, all multiplying e to the minus 2t. But wait, that's 0 e to the minus 2t. So it's equal to 0. There's the proof that that is in fact a solution. You just plug it into the left side of the equation and see that you get the right side for all t on the solution interval, which in this case you tacitly assume it's solution on minus infinity to infinity. All right, how about this? Find an integrating factor on number 4 and use it to find implicit solutions of the DE. Implicit is good. It means you don't have to write explicitly y as a function of t. You just have to find a equation relating t and y that defines a curve as a solution. So how about that one? Number 4, y dx plus 2xy minus e to the minus 2y dy equals 0. Find an integrating factor for that. And implicit solutions. An integrating factor, usually we check first just to make sure that it's not already exact. The purpose of an integrating factor is to multiply this through and make it exact, so you can use your technique for exact equations. Whatever multiplies dx you call m, whatever multiplies dy you call n. And you check, is partial of n with respect to y equal partial of n with respect to x. Partial of n with respect to y is 1, right? Derivative of y is 1. Over here, partial with respect to x treating y as a constant is 2x, right? 2x times the constant y. I'm sorry, 2y, not 2x. Partial treating y as a constant. And over here, derivative of e to the minus 2y is 0, treating y as a constant. So this is minus 2y, oh, they're not equal. So it's not exact currently. I'm going to have to find an integrating factor, as the problem suggests. So here's what you do. We only have two ways to find an integrating factor. There are others, but in general, it's hard to guess. In fact, I mentioned before, you can write down a differential equation that the integrating factor has to solve in order to be an integrating factor and try and solve it, but that differential equation tends to be as hard as the original. Now you've got two differential equations to solve, right? Find the integrating factor of the new equation and then plug it in here to make this one exact on top of that. So people don't tend to use those unless one of these two cases occurred. Suppose I want an integrating factor that's a function of x only. Here's what we said. There will be such if my minus nx over n is a function of x only. So let's compute that. We already have my up here as 1, nx up here is 2y. We divide it by n, which is 2xy minus e to the minus 2y. Oh boy, that's not going to work. That's got a y in it. So this is not going to be a function of x only. It doesn't work. There's one more hope. Our second technique is that maybe there's an integrating factor that's a function of y only. In that case, we need nx minus ny over m to be a function of y only. So we compute that. We already have nx up here as 2y. My up here we already computed as 1. And m is y. Well, let's see. That's 2y over y is 2 minus 1 over y. Sure enough, it's an integrating factor. It's a function of y only. If this expression is a function of y only, then there is an integrating factor, and it's e to the integral of this function, 2 minus 1 over y. Right? So that will be an integrating factor by our proof that we did before quickly in the previous video. Well, integral of 2 is 2y. Integral of minus 1 over y is minus ln absolute value of y. And then you can put an arbitrary constant on here, but I'm not going to bother because I don't need every possible integrating factor. I only need an integrating factor. So here's one when I choose the constant equals 0. Now I have to do less writing than if I picked any other constant. Well, let's see if we can simplify this. This is e to the 2y times e to the minus ln absolute value of y, which is e to the 2y times e to the ln of y to the minus 1 using algebra. And e and ln undo each other, so this is e to the 2y times 1 over absolute value of y. There's an integrating factor for you. And actually, if you omit y equals 0, you can just say on the interval from 0 to infinity, or from minus infinity to 0, we have this. We can choose mu, a function of y, equals just 1 over y, e to the 2y. And forget the absolute value, because actually, on minus infinity to infinity, this says you should use minus e to the 2y over y, but any multiple of an integrating factor is an integrating factor. So we'll just multiply that one by minus 1 if we're on this interval. And we'll just say in either case, we'll choose 1 over y, e to the minus 2y. Then we can consider the equation actually on the whole real axis that way. But this will be an integrating factor on either interval. So let's write equivalently. We go back to the original equation here and say the original equation, the original dE, is equivalent to, we multiply it through by e to the 2y over y. E to the 2y over y times y dx plus e to the 2y over y times 2xy minus e to the minus 2y dy equals 0 times the integrating factor is still 0. And now this becomes, let's see, equivalently, e to the 2. Let's try some of these. This next one is a bunch of substitution methods and separable equations. Let's look at 6c. I said that separable equations is one of the most important parts of the course. I'm going to do a Spoonerism there. Because it occurs a lot. One place it occurs is if you ever take partial differential equations. Those are equations that involve partial derivatives of an unknown function instead of the ordinary derivatives of an unknown function we do in this class. So that's one major application of separation of variables. Let's try dy dx, this is 6c, equals 4 minus x over y. And I give you the hint that it's separable. How can you solve this one? You separate variables. If this, you think of the right side as being a function of y times a function of x, so it's 4 minus x times 1 over y. If it's a function of x times a function of y, then it's called separable. And you can do this, multiply by the reciprocal of the function of y times dx, and get this, y dy equals 4 minus x dx. And then put an integral on each. So you have only a function of y times dy here, and only a function of x times dx here. And this will give you implicit solutions to the given differential equation. The left side is 1/2 y squared by integration. The right side is 4x minus 1/2 x squared by integration. And then there's plus an arbitrary constant I'll call c1. And this gives all implicit solutions, and I'll take that answer actually, but I would prefer to see this. Actually, no, I'm sorry, I said solve it. So if I say solve the differential equation, I don't mean just give implicit solutions that are differentiable portions of these curves. I want you to write y as a function of x. So if I say solve, write y as a function of x, or t, whatever the case may be. But if I say give implicit solutions, then you can do on the last one, just write equations for the curve without writing y as a function of x. Let's multiply by 2 and get y squared equals 8x minus x squared plus, let's call it c, where c is equal to 2c1, is still an arbitrary constant. I don't want to write 2c1, I'll just write c, it's easy, right? Now y must be plus or minus the square root of 8x minus x squared plus c. These are pairs of solutions, one solution for the plus, one solution for the minus, and then also for each c, and the initial conditions will determine c and whether you use plus or minus. These are explicit solutions, that's what I wanted on that problem. How about 6b? This one says this equation is homogeneous. dy dx equals 2y over x plus 1. Sometimes it's not obvious that an equation is homogeneous. You have to kind of fiddle with it a little bit to make it so. This one is pretty obvious. The right side is a function of y over x, right? F of y over x. That's what makes an equation homogeneous. If you put it in normal form, dy dx equals a function of x and y, and it only depends on y and x through the quotient y over x, that's a homogeneous equation. In such, you substitute v equals y over x, a thing you might naturally do anyway, and then dy dx equals v plus x dv dx. If you forget this, you can figure it out from this one because xv equals y, and then you take the derivative, and dy dx, the derivative on the left, put this on the left, equals by the product rule. If you just use the product rule, you get v plus x dv dx. So this comes out of writing xv equals y and using the product rule. But you make this substitution in any homogeneous equation, and it always makes it separable. So let's do that. V dy dx gets replaced by v plus x dv dx on the left, and then 2 times v plus 1 on the right. Once you be able to do these separable equations, they're extremely important and they're fairly easy. Now I subtract v from each side. I've got x dv dx equals v plus 1. And see, it's separable. That's the purpose. Make the substitution, you always get a separable equation. So you look for that after you apply this substitution. Now I'll divide by x times v plus 1, and also multiply by dx, and I get this. 1 over v plus 1 dv equals 1 over x dx. Just by algebra, I separated the v's with dv and the x with dx on each side of the equation. Now, by our previous analysis, we can slap integrals on there, and these will give us implicit solutions to the differential equation. Well, this one, how do you integrate this? You substitute u equals v plus 1, and du is du dv dv. Oops, du dv dv, but du dv is just 1, so this is actually just dv in this case. So you replace dv with du, and this was 1 over u. You got integral 1 over u to u equals integral 1 over x dx. Well, we remember from calculus that this is ln absolute value of u, and this side is ln absolute value of x. Then there's an arbitrary constant of integration. So there is the solutions. Now you put back u is equal to v plus 1, so you've got ln absolute value of v plus 1 equals ln absolute value of x plus a constant. V, however, was y over x. A lot of substitutions to go back, so it's ln y over x plus 1 equals ln x plus a constant. There are implicit solutions. I think you can leave it there for the exam. It is true that you can use your properties of logarithms to combine these. You might prefer to put it like this. Ln of y over x plus 1 minus ln of x equals c. And now I have to go to the next page, apparently. Remember, you can combine logarithms. The difference of the logarithms is the logarithm of the quotient. So this is now ln of y over x plus 1 over x equals c. Just combining the logarithms by algebra. And let's see, this is, take ln of each side. Well, let's do this. Ln of y over x squared plus 1 over x equals c. Take e to each side, and you get equivalently y over x squared plus 1 over x equals, absolute value thereof is e to the c. This is an arbitrary positive number, right? And then you take the absolute value away, you find out that y over x squared plus 1 over x is equal to an arbitrary, y over x squared plus 1 over x is equal to plus or minus e to the c, which is an arbitrary number a, let's say. A equals plus or minus e to the c. And what's more, if you go way back here, when we separated variables, we assumed when we divided through here that this y wasn't equal to 0. In fact, if you go back to the original solution, let's see if y equals 0 is a solution. Looks like it's not in this. Number 7 from the practice test. A few of you have looked at this online already, discussions. Suppose I want to not solve this differential equation, but qualitatively discuss its properties, right? dy dt equals minus 2y squared times y plus 4. This is what we call an autonomous equation because the t is on the side, only the dependent variable y. One way to qualitatively discuss how the solutions behave is to look at its phase line if it's an autonomous equation, and whether or not it's autonomous, look at its direction field. So I asked you to do both to this one. To sketch the phase line, let's first start off by sketching f of y versus y, where f of y is the right side of the equation in normal form. dy dt equals f of, in general, ty. What does that function look like? Z equals this function of y. Well, it's a polynomial, right? If we multiply this out, it's minus 2y cubed minus 8y squared. A polynomial is the number times the whole power of y in this case, plus a number times the whole power of y, plus dot, 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 plus a number in general. But numbers times whole powers of y all added together is a polynomial of y. Well, remember the properties from algebra. If we plot z as this polynomial function of y, where, wherever this is equal to 0, you have an intercept on the horizontal axis. So when y equals 0, that makes this factor 0. When y equals -4, that makes this factor 0. We have two intercepts along the horizontal y-axis at 0 and -4. Now this is a 0 multiplicity 1. In other words, this factor of y plus 4 occurs one time, right? In that case, what happens, if you remember sketching polynomials in algebra, is the function crosses the axis here. But here we have one of even multiplicity, and an even multiplicity, the polynomial bounces off the horizontal axis. So, and it becomes a horizontal tangent line. So we know that the polynomial, whatever its sketch is, only touches the axis here and here. It crosses on this one, and it bounces off on this one. What else do we know? If we write this out, we can use the dominant term analysis and say minus 2y cubed. This is the dominant term because it has the highest power. Since it's got a negative coefficient, it's going to go down on the right? And then since it's an odd power, it'll go the opposite direction on the left. So the end behavior, you call it in algebra, take a look at your algebra book if you've forgotten, is to go down on the right, steeper and steeper, and go up on the left. And so we know it goes like this. We know it touches at these points. We can sketch it pretty well just by drawing a curve like this. Because from calculus, you know, a third-degree polynomial has at most one maximum and one minimum, right? You can take the derivative, and it's a second-degree polynomial. It only has two places where the derivative is equal to 0 at most. So there they are. This point and this point must be the only places where you get a peak or a valley to this thing. You don't have to sketch this accurately, and you can use your calculator if you want. You just have to make sure you capture all these important points here. Sometimes you don't know, what interval to plot on, so you want to check these at least by hand, not just do it by calculator. But calculator can be very helpful still. Here's what it behaves like roughly. We don't even need to put any numbers. What we need to know is this. Over here for y greater than 0, z, this right side of the differential equation, is negative, right? It's down here, below the y-axis. Since this is negative, dy dt is negative in the solution, which means when I plot the solution, y is going to be decreasing as a function of t, right? Dy dt is negative, that means y is decreasing. So when I actually sketch it, I know the y value is going to get smaller and smaller. Now down here I'll draw the phase line, which is the y number line. I should label this with a y here. And let's do it just to be complete. And the idea is you're writing parametric curves on there. You're writing y as a function of t, but just plotting y. And so I plot these parametric curves in one dimension, since it's a line, going this way because y as a function of t is decreasing. So if I let t increase, y will move this way because dy dt is negative. Now in here, between -4 and 0, I just draw the phase line directly below. I like to draw these points straight below to help me. Over here in this interval, y between -4 and 0, again, this function is negative, so dy dt is negative. That means y as a function of t in the solution will decrease, so I draw an arrow this way, meaning if I plotted y as a function of t and let t evolve, you move along the y-axis in that direction. But over here, y is positive, z is positive, that means dy dt is positive, so a solution, if you started here, would move this way, and towards -4. Now what you do is you take there's the phase line, here's the two critical points, or any points where you touch the axis. Critical points mean the right side is 0, that's what a critical point is. That's going to be where it touches the axis here, and just bring those down. There's two critical points, and then you use these arrowheads between the critical points and on the ends of outsides of them to determine what kind of critical points they are. Here this says if you start with y positive, you'll move towards 0, but if you start with y negative, you'll move away. That's a semi-stable critical point. Here you move towards the critical point on both sides. That's an asymptotically stable critical point. If it moves away on both sides, that's an unstable critical point, because if you start near here as t, time, think of it, evolves, you'll move away from there. You won't stay there, stay close to it. So that's unstable. Now, once you have that, you take the phase line and you turn it vertically. Here it is. And then you can sketch the solutions in t, that's the y equals 0 line is t, y plane. So I should maybe label that t and y, just to be complete here. The t-axis and the y-axis is the solution space. That's the last part of the problem. Sketch a few solutions using the phase line. Well, the phase line, I turn it this way and put it next to the y-axis. So here's y equals 0 corresponds to this point. Any place where there's a critical point, an equilibrium point it's sometimes called, you draw a horizontal line because that turns out to be a solution, right? Any constant value of y that makes the right side 0, like y equals 0, is also a constant solution because its derivative is 0. Derivative of a constant is 0. So derivative is 0 is 0, 0, y equals 0 makes the right side 0, y equals 0 is a horizontal or constant solution. Similarly, y equals negative 4 makes the right side 0. The derivative of negative 4 is 0, so y equals negative 4 is a constant or equilibrium or stationary solution. So those are your two stationary solutions, constant solutions. And now the other ones, you know from the phase line what happens. If you're up above y equals 0, the solutions as function of t have to move down. So this here is the projection of these curves onto here. You take this curve, it projects over here. And as you move, and you're saying that as t goes forward, you're going to go down towards this curve. That's what this arrow tells you. In here, between 0 and minus 4, you have to go down. And over here, you have to go up. But these can't intersect by the existence of uniqueness theorem, right? This is a continuous function of y, and our existence and uniqueness theorem says if this is continuous, the right side f, and df dy, partial of f with respect to y, is also continuous, then there exists a unique solution to this together with any initial value, which says any point you start, you can't go and intersect any other solution, it just has one solution. So if these intersected, there would be an initial value point right there where there was two solutions passing through. You violate uniqueness. Existence says there's a solution through every point, right? What point you pick, that corresponds to an initial condition, and the existence of uniqueness says there's a curve going through that point. So the idea is that these solution curves fill up the whole ty plane, since this f and df dy are continuous everywhere. There's a curve going through every point, and no two curves intersect. So these have to just asymptotically approach the stationary solutions. And down here, since the arrow is up, these move up towards the stationary solution. Since these go down, these move down towards the stationary solution and asymptotically approach them on both sides. Up above here, you asymptotically approach this. This is the qualitative analysis. If you start with an initial condition, y of 0 equals 1, that'd be about here, right? T equals 0 here, and y equals 1 about here. What's going to happen? You're going to go down, 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 like that. You will asymptotically approach y equals 0 if that's your initial condition. If your initial condition is here between 0 and minus 4, that says you'll go down, down, down this curve towards y equals minus 4. And if you start with the initial condition down here, you'll go up. An initial condition doesn't have to be at t equals 0. It's whatever your y of t0 equals y0 condition is. And so it can be a point out here, but wherever you start, these tell you what the long-term behavior is. It's either towards 0 or towards negative 4, depending on your initial condition. That's a pretty strong conclusion without solving anything. The curves behave like this, or this, or this. What's more, because this is autonomous equations have this property. Y of t is a solution. That means y of t minus c is also a solution. You get, by translating this over c units. Alright, so this, and you translate it over any number of units, it's again a solution. So all these curves up here are identical, just like a rigid wire, shifted over, shifted over. All the solutions up here behave like these two. These are just examples of typical solutions up here. Here's some examples of typical solutions in here. They're all the same shape, just slid over, and these are all the same shape, just slid over. Isn't that a nice conclusion? You can draw quite a lot of knowledge out of just looking at the differential equation. Well, problem 8 here is what do you do if you can't solve a differential equation and qualitative analysis isn't good enough? You run to the computer and let the computer estimate the solution. Euler's method is a very simple method that people don't use so much in practice, but it's okay for a by hand rough estimate for a little while. And the other numerical methods are often very similar. If you take a numerical methods class, you can learn about these. But this illustrates what goes on in numerical methods, so lots of books, most books, like to put this one in because it's a simple presentation. Suppose I want to estimate numerically by Euler's method a solution of y prime equals t plus 2y with initial condition y of 0 equals minus 1. This has a unique solution, right, by the existence of uniqueness theorem. And suppose I want to estimate the solution on the interval from t equals 0 to t equals 1 using 2 steps. So I first compute the step size. We often use h, sometimes delta t, is the interval length b minus a divided by n, the number of steps. So if I go from a equals 0 to b equals 1 and n equals 2 steps, it's 1 minus 0 over 2, 1/2 increment per step for 2 steps to go from 0 to 1, obviously. Duh, all right? So you don't have to do all this figuring. I just put it so you see the formula for a harder problem, right? From the initial condition, you get t0 equals 0 and y0 equals minus 1. Then Euler's method says you are the machine and you evaluate y at ensuing values of t as yn plus 1 equals yn plus h f of t n yn. That's what we got by doing that. We derived it. That tangent line approximation to the next point on the solution curve. And while t, meanwhile, is just incremented by step size h each time. You don't have to use fixed step size, we said, but for our examples, we'll do that just to keep it simple. All right. So t1 is then t0 plus h. We just increment it by h equals 1/2. 0 plus 1/2 is 1/2. So we start at t equals 0, we go 1/2 unit to t equals 1/2. y1 by Euler's formula here, Euler's numerical method, is y0 plus h times f of t0 y0, because we're using n equals 0 in Euler's equation for a numerical solution of the differential equation. So it's y0 plus 1/2 f of t0 y0. Then when we'll put in n equals 1 and then compute y2 is y1 plus 1/2 f of t1 y1. And if we went further, we take y3 as y2 plus 1/2 f of t2 y2, and so on and so forth. We just do that over and over until we reach the end of the interval. I just did 2 steps to make it simple. So we take y0 plus 1/2, and then if f is t plus 2y, then f of t0 y0 is t0 plus 2y0, right? So I've got y0 plus h is 1/2, y0 plus h, f is t0 plus 2y0 is 0 plus 2 times minus 1 for the initial condition that we had up here. And when we take minus 1 plus minus 1, we get minus 2. So y1 is minus 2. Now we put n equals 1. We're going through a little loop here. Euler's method is an algorithm. Now we increment t again. t2 is t1 plus h is 1/2. We're at 1/2. We add another step size of 1/2. We get to 1, the end of the interval. y2 correspondingly by Euler's method here is y1 plus 1/2 h f of t1 y1. Where f is t plus 2y, so we put t1 plus 2y1 here. Well, from our last step, y1 was minus 2 and t1 was 1/2, and so we just put those in and we calculate, we get minus 15/4, or minus 3.75. After a while, these things get too complicated to keep fractions. Usually just write decimals like a computer would. And we can summarize this saying here's n versus tn versus yn. Here's the initial condition. N equals 0, we get t0 y0 that we started with, right? 0 minus 1. At n equals 1, we got t1 is 1/2 and y1 was minus 2. And then when n equals 2, we get to the end of the interval, t2 equals 1, right? Here. And y2 was minus 15/4. This table gives 3 points that are supposed to approximately lie on the actual solution of this. Because they're tangent line approximations, they're not exact usually. Here's number 10. This is an existence and uniqueness problem. Suppose I have the differential equation y minus 1 squared dy dt equals minus 2t, together with the initial value, the initial condition, y of 0 equals 2. How can I solve that? You look at your different methods and you say, well, it's not linear because I have to be able to write it as dy dt plus p of ty equals q of t, and I can't do that because there's a y squared, for instance, in here, right? So it's not linear. Maybe I'll try and see if it's separable, right? Well, if I multiply by dt, I notice I can separate all the y's with dy here and all the t's with dt over here, so it is separable. And then our theorem says we can integrate both sides and get implicitly solutions. So I integrate both sides. The integral of 1 minus 1 squared is y minus 1 cubed over 3. And the integral of minus 2t is minus t squared. And then there's an arbitrary constant from each integral. I'll just put them both over here. And this actually can be solved for y as a function of t, right? I multiply by 3, I take the cube root and add 1, and I get, multiply by 3 and take the cube root, I get this. And then I add 1, I've got the solutions are y equals 1 plus cube root of, if I call this 3 times the original constant, an arbitrary constant c1, right? 3 times the original constant, we'll call c1. It's still an arbitrary constant. I get this, y is 1 plus cube root of c minus 3t squared. So, problem solved, right? Well, what interval is the solution good on? It doesn't tell us that, does it? We'll apply the existence and uniqueness theorem. And first let's apply the initial condition y of 0 equals 2. And that means we plug in 2 for y and 0 for t in here, and we get 2 equals 1 plus c1 minus 0, right? Oh, that says c1 must be 1, so you add 1 and 1 and get 2, right? So c1 must be 1, and that means you put it into here in the unique solution to the initial value problem. The differential equation together with the initial value is called an initial value problem, is y equals 1 plus cube root of the quantity 1 minus 3t squared. There's our solution. Now we'll say it's solved, and on what interval is that a unique solution? Well, we'll apply the existence and uniqueness theorem and say it's good at least on this interval. It might be a larger interval in general, but the existence and uniqueness theorem, guarantees us go. Gotta put Murphy's law in here somewhere, right? So there's our solution up at the top. The existence and uniqueness theorem says if we put it in a normal form, which we can do by dividing through by y minus 1 squared, this is the original differential equation divided by y minus 1 squared. It says for this differential equation, which is equal to the original one except that y equals 1. We know that there will be a unique solution for any initial value, such as the one we're given, where f, the right-hand side in normal form, and the partial of f with respect to y are both continuous. So we look at this and say, oh, it's a polynomial t divided by a polynomial y, continuous divided by continuous, is continuous provided the denominator isn't 0, right? So anywhere except y equals 1, f is continuous. Then you take partial with respect to y, you get 4t over y minus 1 cubed, and you decide, oh, polynomial over polynomial, that's continuous except where y equals 1, making the denominator equal 0. Now, we have to be a little careful. This one we divided by y minus 1 and found out that's the place that's undefined. It could be the original differential equation solution are good at a bigger interval, but this is all we can say with the existence and uniqueness theorem, is that this solution we got will be, will provide a unique solution on an interval that doesn't include any points where y is equal to 1. Where are those? Well, we just say, well, y equals 1 means this is the square root of 0. So it's where 1 minus 3t squared is equal to 0 that it might become not unique, which is, solve that algebraically, y equals plus or minus 1 over square root of 3. We know from the existence of uniqueness theorem that this solution we found is unique, at least on the interval that excludes t equals plus or minus square root of 3. The interval that includes the initial condition at t equals 0 and avoids these 2 points goes from minus 1 over square root of 3 to plus 1 over square root of 3. So it's good on at least that interval. It might be a bigger interval, but if you look at it, at t equals plus or minus 1 over square root of 3, the slope of this goes to plus or minus infinity, and so actually that's all that's good on. The derivative doesn't exist at these endpoints. Here's a tricky existence uniqueness theorem, number 11. Suppose we want to say, here's a linear equation without even finding the solution, because this looks too hard with secant t in here. if we maybe solve it by Euler's method or some numerical method, what's the biggest interval in which we can guarantee a unique solution? After all, we could crunch numbers with our numerical method forever and let t go on and on and on, but would the solution be any good? Maybe the solution isn't unique out there or doesn't exist or something. It's nice to give your boss a big page of crunch numbers for a solution that doesn't exist, right? So on what interval can we guarantee our numerical method or whatever method will give us a solution that makes sense, that exists and is unique, right? So what we can do is we'll take this differential equation. We don't have a theorem for a differential equation in this form, but we do notice it's a linear equation because we can divide through by t squared minus 3t minus 4, and now it's dy dt plus p of ty equals f of t. It's a linear equation, right? dy dt plus a function of t times y equals a function of t is a linear equation in standard form. And actually this is linear also, just not in standard form. We put it in standard form because we have an existence uniqueness theorem for it when it's in this form. It says that when p and f, this is a stronger theorem than we had for nonlinear equations. For a linear equation, you say if p and f are both continuous on an interval that includes the initial point, then there exists a unique solution to any initial value problem on that, including this one on that interval. Any initial condition whatsoever in that interval. So let's try it. Where are these continuous? Well, the zero function is continuous everywhere. We just have to worry about this one. Secant t is continuous within its domain, which is where t isn't pi over 2 plus a multiple of pi, right? You have asymptotes there for secant. And a division by a polynomial is continuous except where you divide by 0. That's at minus 1 and 4. So we know that we need an interval that includes t equals 0, the initial point, and excludes all these. What's the biggest interval we can construct? Well, we can go from minus 1 to pi over 2 to include the initial point and exclude all of these. Here's the biggest interval on which you want to give your boss the solution. Finally, here's a homework problem. I think I'll attach this because we need to put some problems on the practice test that have exact equations and integrating factors. And actually, if I give you a problem on integrating factors, you have to solve the exact equation too. So, good chance I'll give you an integrating factor from the final. So, if you saw this online, you already know how to do this. This is just a replay. But suppose I have this equation here, 3dx plus y times x plus 1 dy equals 0. This one actually is separable. We could solve this one with separation of variables, but I just tried to give a simple example of an equation that also works with integrating factors. And there are lots of equations that can't be separated, but you can still use an integrating factor. So let's solve this by integrating factor. And first thing we do on these is we check, maybe it's already exact, I don't need an integrating factor. Whatever multiplies dx is called m, a function of x and y in general. Whatever multiplies dy, a function of x and y in general, is called n. If partial of m is equal to partial, with respect to y, is equal to partial of n with respect to x on an open, simply connected region, then we say this, we know by theorem this is an exact differential, it's d of something, and we can solve this as an exact equation. But my is equal to 0, right? Derivative of the constant is 0. Partial of this one with respect to x, treating y as a constant, is just y, and those two aren't equal, so this is not an exact equation. We'll have to find an integrating factor that makes it exact. That's the purpose. You multiply through this equation by some function mu, in general of x and y, that makes this exact. Well, the only easy cases are when mu is a function of x or y only. Let's try for an integrating factor that's a function of x only in this case. There will be an integrating factor that's a function of x only if my minus nx over n depends only on x. So you compute it. Here's my, we already computed, 0. Minus nx, we already computed as y, all over n that's staring us in the face up there. And we divide that through and get minus 1 over x plus 1. It is a function of x only. We know that there's an integrating factor, mu equals e to the integral of that. Right? So, x only excited, right? Because we got lucky, right? So e to the integral of minus 1 over x plus 1. Pull the minus 1 out. To integrate 1 over x plus 1, we make a substitution. U equals x plus 1. Du is du dx. Dx is 1 dx. So we replace dx with du and 1 over x plus 1 with 1 over u and pull the minus out. And we have this one, an integral 1 over u is the absolute value of u. Be careful to put this in. Sometimes you need it. And then find out later if you can get rid of it or not. then minus 1 multiplying can go up in the exponent by algebra. This is e to the ln absolute value of u to the minus 1. E and ln are inverse functions, so you just get absolute value of u to the minus 1, or 1 over absolute value of x plus 1 out of that, since u was x plus 1. Alright, so there's an integrating factor. Now it turns out we didn't need those absolute values, because after all, we're only going to be solving this on the interval x greater than minus 1. That was one of the initial stipulations. It did that because we were going to have to divide through by x plus 1, and then we wouldn't have solutions valid there anyway, necessarily. So the integrating factor is 1 over x plus 1. I'll take the original differential equation, multiply it through by 1 over x plus 1, and I get this, multiplied by the integrating factor. Now it's supposed to be exact. That's the idea of the integrating factor. If I didn't blunder, it will be. Let's see if I messed up or not. This is my new m, this is my new n, and now partial of m with respect to y is nothing, because x is treated as a constant. And partial n, y with respect to x is also nothing. Sure enough, it's exact, and y equals nx. That means once it's exact, here's how you solve an exact equation. Phi is the integral of whatever multiplies dx with respect to x, and it's also integral of whatever multiplies dy with respect to y. And these two have to be equal. Will it be equal? Yes. Exact means that there is such a function, that this is d phi dx for some x, and this is d phi dy for some function phi. So we integrate both of these. This is a partial integral with respect to x. We already found out integral 1 over x plus 1 is ln x plus 1, and the 3 comes out and multiplies it. Integral of y is a half y squared. In this one, because it's a partial integral, you can add on as the arbitrary constant any function of y, because y is treated as a constant. On this one, add on any function of x, because x is treated as a constant in a partial integral with respect to y. These two are equal. We wouldn't have found out they're exact if they weren't. How can we make these match? Well, this must be part of h of x. This must be part of g of y. We must have 3 ln x plus 1 plus 1 half x y squared. Plus, you can add any c into each of these. It doesn't depend on either x and y. This is the most general function phi, for which this is d phi dx and this is d phi dy. You can check it and plug it in, right? It satisfies both these conditions. This is the most general function that satisfies both of these. We can leave the c off for our purposes because we know the solutions are phi equals an arbitrary constant. If we have an arbitrary constant on both sides, we can just combine them. So the general, we'll choose c equals 0 just for simplicity, and then we'll say this equals an arbitrary constant is implicit solutions to this differential equation.